Dobro večer svima. Dobrodošli na još jednu meetup sesiju kod Centrika Novi Sad. Drago mi je što ste došli u velikom broju. To samo znači da radimo dobru stvar iz meseca u mesec. Ovaj meetup će bude malo drugačiji što se tiče jezika, bit će na engleskom jeziku. Nadam se da to neće predstavljati problem za vas. Tako da ću sad da nastavim na engleskom. Hello everyone, I wish you a warm welcome here at our CodeCentric offices. It's really nice to see you coming from month to month, which gives us a good signal that we are doing a very good thing and that you like what we do. I wish to especially thank my colleagues that really make these shows and these meetups really nice, and they put a lot of effort in presenting interesting stuff. So, who I am. My name is Toplica Tanaskovic and I'm IT consultant at CodeCentric, and my field of work is high performance data processing, computing, and that's done today in C++ and related technologies. So that's what we are going to talk this this meetup. So the title might be a little bit intriguing. So title is When Threads Are Not Enough. During the late 80s and 90s and maybe early 2000, people thought that threads will solve everything. For that time, they were solving pretty much stuff, but nowadays they kind of create a lot of problems. So I want to talk about that, how to overcome such problems and what to do. I will give you a few examples. I will present you the library that was developed by one of my friends. It's an open source library. I've also contributed to it, and we are using that at one of our clients in a very large scale. So let me begin. In traditional data processing, we have a pretty clear situation. When you have to do some processing, some calculations, some data fetching, and if that takes a very small amount of time or reasonably small amount of time, you usually do that in the same thread. However, if that duration is long or in some cases not deterministic, then you always use a separate thread. That covers almost 99% of traditional use cases, and it works. And it worked so far. However, in modern data processing, the huge sheer size of the internet and the data available to data centers and the companies grew exponentially. So we ended up with a situation where we have a lot of concurrent requests. We use the various data sources, and what's the biggest problem is you don't control processing time anymore. So we cannot do anything about this. It's good that we have a lot of concurrent requests. This is also good because it allows you to have failovers and choose the better data sources. But this is something we must address because it creates a huge problems when you want to serve a lot of customers. So, what affects the processing time? The processing time has two major contributions to it, and one is the calculations that you do. And we will assume that your algorithm and calculations are sane and stable, and that they always take the same time. And when I say always take the same times, it means that when you look at individual work unit, you have a set of data and you want to do some calculations or some processing, it will always take the same amount of CPU cycles or same amount of time, regardless whether you're doing that in a main thread sequentially or you're doing in a separate thread. If some calculations take, 200 CPU cycles, that will always take 200 CPU cycles. If those calculations are not stable, if your algorithm is not stable and the calculation time varies from time to time, even if you have the same input data or the same set of data, then you probably have bigger problems than threads. So Let's assume that your calculations are stable and that they always take the same amount of time. When I say the same amount of time, I want to emphasize it's a thread-wise. So no matter which thread it executes, it always takes the same number of CPU cycles. The other thing which we do not control, and usually we cannot affect at all, are things that are not under control, which means various data sources, pieces of hardware, pieces of computation hardware, I don't know, web services, you name it, everything is used today. So what are we going to do? First of all, there is no magic here. That's the most important thing. We cannot speed up the calculations. If you have, for example, let's just give a small example. If you have 3 numbers and you need to calculate the average of that 3 numbers, that's it. You cannot improve that. You just add them, sum them, and divide by 3. You cannot improve that. So what we can do, we can minimize blocking, especially if you're running in multiple threads. That's one thing, that's common sense. The other thing is, what people often forget is that they need to improve the through output. If your response time is small and you're fine with it, it means one thing, that you're processing data fast, but that does not always mean that you can serve a lot of requests at the same time. Basically, I've seen numerous pieces of software and server software that has, let's say, response time of, let's say, 2 milliseconds, but they cannot serve more than, I don't know, 20 or 30 concurrent requests. So the second part we must address is to improve the through output. And the third part, which comes together with improved through output, is to improve reliability. Because when you have a huge number of requests to process, and if you fail, the requests are going to either pile up, or you will have a bad name on you and you will lose your customers. So let's assume that we have a pancake shop. So we have a worker, we have a customer, we have packaging table. We assume that our worker is very fast, very knowledgeable, and that he can pack the pancake on a table at fixed time. So he takes, let's say, that it takes 30 seconds to pack, put the jam or Nutella, pack it and serve. What we don't control, this is Acme pancake machine. So because customer will come, I want thinner, I want thicker, I want bigger, I want smaller. So the time needed for pancake machine to give you a pancake is not deterministic and it's not stable. So what's happening? Customers pile up because our worker asks the first customer, what do you want? He says, I want this pancake. And he sets the machine, then he waits for the machine, picks up a pancake, goes to packaging table, serves him, and goes to next. He might be fast, but he cannot serve a lot of concurrent people, and the requests pile up, so the customers pile up. They're not served, so they get angry and they leave, and what happens? The shop goes out of business. So let's see how can we improve this. Maybe we should hire another worker. Sounds reasonable. They can work in parallel. But what happens? We have concurrency problems, which means we have fight for resources. We might end up in race conditions, even in deadlocks, unnecessary waits. So customers leave, we serve even less customers, shop goes out of business again. So what can we do? We can do, let's say, we can do pooling. We go to for one customer, say, what do you want? He says, I want this pancake. Then you go to the pancake machine, you set it up, you come to the second customer, what do you want? He says, I want this. He goes, sets a machine to create another pancake machine. He gets to the third customer, I want this, and goes to pancake machine, checks whether the pancake machine finished any of the previous pancakes, If it is, go package, serve it, vice versa. Well, that creates problem because the worker has to remember a lot of data. He has to somehow keep track of each customer order, and that data can pile up. By the way, this is so 90s, I like to say. You know, pulling and busy waits are not nice way to do it. So, what are we going to do? Our solution is to employ event-based task system. So, basically, it's what is event-based task system? That's something like the same event-based paradigm where you react on events. However, we don't have simple callbacks. We have objects in there. We like to call them tasks that are self-contained and independent objects. They track their own state, so the worker, in our case thread, does not have to take care what's going on inside. They can react on all events or on a specific events. They can even be periodic if you want to have something like timers, etc. And what's most important, they're non-blocking. They must not block. So, how did we achieve that? Well, in the 2000, few people, Douglas Schmidt, Carlos Ryan, Michael Kirchner, and Irfan Piarali, they've invented this leaders followers pattern. So, and they published the paper in 2000. Yeah, I think it's 2000. And basically, what it means that you can have several workers, let's call it the real name now, several threads. And what's the general idea? The general idea is that you have one leader thread which waits for event to occur. When the event occurs, he demultiplexes the event, sees what needs to be done, starts doing it, and promotes one of the following, the dormant threads, to a new leader, if they're available. If they're not available, he returns to be a leader once again. This is the only, so in one point of time, there can be only one leader thread, and when it gets an event and starts processing, that's the only time when you can have a concurrent processing of multiple threads. Basically, that can happen all the time, but that's the only time when you can start such an activity. So, let's go to the actual implementation. As I've said previously, one of my friends and colleagues, he created a tasks library. It's called libtasks. This is URL. So that basically employs this leaders followers pattern and solves a lot of problems for I/O operation and non-deterministic data processing. So we started with a very rudimentary library, then we improved it, and now what we can achieve in production at certain phases, we can have responses that are measured in below 200 microseconds. It currently supports all kinds of I/O tasks. You can implement high-performance web backends, implement Thrift servers, and also you can implement HTTP clients, which are they might be useful for accessing web services, but they're good as an example how I/O processing should be. So let me show some of the examples. The core of each and every task, and it's something that handles the data. So there are various handler-based classes. Now this is one that's most common in use because a lot of times, even in the databases, NoSQL databases, which are supposed to be high performant, like Couchbase, you still get JSON-like and REST-like response. So this might be a good idea. So what it has a handler response, which returns a Boolean value, which basically means, do you need to process more data or you're done? And this is how we make a simple HTTP request towards the Google. So we have a sender, we have templated our test handler, that's one here, then we create a request, and then we send. When the response comes, this gets called, so you can do anything you like with the data. What's important to say that this does not block. The execution of the current context thread continues. Another way we can use this, I don't know how many of you heard about Thrift Protocol, and maybe some of you used the protocol. Well, the Thrift Protocol is a binary, something like a binary web service. It was developed by Facebook to improve throughput and to stop wasting network traffic by sending unnecessary data, which usually SOAP and even REST sends a lot of unnecessary data. So I won't go into much details about the Thrift. You can read it about. Basically, it accepts the processor, and this is how we create a server. This is a handler that handles request. It has one method. We do some with the data, return data, and this is how we start it as a server. We create a task, which is our acceptor, and we give it our processor there that will process the data, and we make it Thrift, and it will listen on this port, and then we just join if we want to have if we want to have it run as a server mode. So our solution, let's address the first thing. We don't use any blocking calls anywhere. You don't have to use the libtask library if you want to design something on your own, or you have something to solve and you see that, for example, libtasks or even plain libev library from C is overkill. You must follow a few simple rules. So you must not use any blocking calls. Sometimes people say, okay, I'm not using blocking calls, but what I do, they use non-blocking versions of, let's say, system calls, but they use busy wait. They're in a while loop, say. So what should you use? You must use event loop and signaling, and this is weird. You run single-threaded. Why? Well, when you run single-threaded, you remove a lot of problems you have. You don't need to lock the data. You are not afraid anymore of race conditions. You know that at a certain point of time, only one thing, whether it be thread or whatever, accesses the data. And also it removes a lot of headaches if you are using non-thread safe libraries. Most of the NoSQL libraries that you have to use on a daily basis are utterly not thread safe. The typical example of library that is not thread safe and that creates more problems than it brings value is the library that connects to a Couchbase. That's a typical example. So if you run single-threaded, you avoid a lot of those problems. It does not mean that you won't have any problems, but you can minimize that. Okay, so how do we improve throughput? Since we are not blocking, we are free to do other stuff. So don't wait for slow data to arrive. Accept other requests. Also, what is most important, and it's often forgotten, if the data does not arrive on time, don't wait for it forever. Just politely say sorry to the client and don't keep him waiting forever. So it's better, sometimes it's better to have timed out and failed request than to stick and wait for some very slow data source, or maybe there is some problem like NFS or something like that. You will wait forever, waste resources. And the other thing is to spread the load. Don't have one process that does things. It doesn't have to be a multiple servers. Physical service can be on one machine, but spread the load. Because often forgotten when you do high scale and high performance processing is that requires a lot of care and a lot of tweaking of TCP/IP stack if you're going outside of the local machine. So if you don't spread the load, the system will get overwhelmed and you might come into unfavorable position of the traffic shapers and TCP/IP schedulers. And how do we improve reliability? We use load balancer. We always use load balancer. And we also run multiple single-threaded instances. I've explained why we should use single-threaded instances, and when you use load balancer, it actually does not make sense unless you run multiple single-threaded instances. However, you must pay attention when you're choosing your load balancer that it must be capable to see whether your service or instance or process is dead or not responding, so it will skip it for a certain period of time. They can tweak, for example, Nginx supports that. If you connect through Unix domain sockets, they have problems with TCP/IP load balancing implementation when you use UWSGI backend. Cherokee supports it. Apache has its own problems with threads, so it's not so good for this kind of stuff. So basically your architecture should look something like this. You have end clients coming, you have Nginx or Cherokee or whatever as a load balancer, and you have services in the background. So how it does, you can tweak it, but we found out through our experimenting and a lot of measuring that simple plain round robin algorithm employed by Nginx is usually the best, the most simple. So first request goes here, second here, and go in cycles. If this one dies, it will try to contact it, see that there is no response, unable to connect, it will serve from the another one. Also, it will check after a certain period of time whether this guy woke up. If he did, he'll start using. So I've prepared a small example. I like to call it Pancake example. Basically, we have a service handler that accepts thrift requests, and they want some results, and it's rather simple. We get the string as a question and we return an integer as a response, and we will simulate the data source with a relatively slow web service running on our local machine. So this is how we create a handler. So basically, when the request comes, this method is called, and this structure, the share pointer to the structure, has all the arguments. So what we do, we create a handler with our response handler. We bind a few callbacks, so just to know whether the answer is ready, or maybe the system failed, so we don't know the answer. We create a sender, we create request, and we send request, and we're ready to accept a new request for data processing. So once again, this does not block. So when the handler processes the data, receives and processes the data, it will either call this callback answer ready, which will give us the result. We call finish, send the result, or if it does not know, or maybe failed, we just return empty answer. We can, however, you can improve this, by adding some additional diagnostic data, but for the sake of example, this is enough. And this is our response handler. Basically what we have two type definitions for callback functions, and what it is, it's a constructor, and this is the method that handles the response. It gets the response, we check whether it's 200 okay. If it's not, we call the failure callback. If it is okay, in our case, we just return the content line. So, and we here return false. Once again, we return false here because the return value of this handler response method tells, do you need to do any more processing or not? If you return false, then it means that you don't need to do any more processing and that you're done. And that's basically the simple example how to use non-blocking mode to access a slow data source while not sacrificing your through output. Your response times will still depend on how your slow data source is, but you will increase your through output, which is a huge benefit. So I will show you, I've prepared an example of this so you can see it running. So basically, okay, this is our web service which returns random JSON string, and we here started two Meetup server instances, each having one worker. I said we run single threaded. This 0 is just an identifier, so we can see that they're different. And the Nginx is running in the background, serving them. So let's start sending requests. We are generating requests with 2 threads. So right now, even if the web service is written in Python, sorry, I forgot to sync the output of to the console. So sometimes the output will be borked. We are still serving on this laptop around somewhere below 3,000 requests per second, having 2 server instances, and Nginx has load balancer. So let's see what happens. We kill this one. We don't get failure. So we see a penalty in processing time, so the responses are now around 900 microseconds, and we also process not half, but maybe 60% of the original data, but we don't have failure. That's important thing when you do a large-scale processing. And if we start this again, it will pick up at a certain point of time. I guess it takes, I think I've configured it to about 10 seconds or so. There you go. See? We return to the original processing speed. Okay. The code examples, they will be available on a GitHub. I will post it on a Meetup group, but you have a lot of examples of this type of processing in LitTask library itself. It has a lot of unit tests that can you use as an example. There is also a lot of examples over there, and these are some, if you want to see how to configure Nginx for such stuff, and how to use Thrift and UWSGI, or maybe you want to read the paper of the 4 professors that invented leader followers pattern. There is a link. This presentation will be available online, as I said, in the next few days, so you can access it. I hope that I didn't bore you to death with this talk. I wish to thank you all for paying attention to this. And do you have any questions about this?
You mentioned several times some load balancing. So can you tell us a few words about that?
Well, load balancing, let me get back to this. It's here.
It's Nginx?
Yeah, that's Nginx.
Okay.
You can put Cherokee. Basically, you can put anything you like. You can make it custom make, but Thrift has some nice ability to go through HTTP, so it's naturally to use some web server for that supports UWSGI for communication with the backends. However, it's important to say that this will not work as good with Apache, because Apache is not web-based. It's worker-based and deploys threads, so it has to be some web server implementation that is event-based, like Nginx or Cherokee. Yes?
Do you consider the Akka or Vertex or something like that? So you start with C++, why, and why JVM started with after that?
Okay. Why C++? Because it's simply fast. There is no preference here towards the technology or anything else, so we are not this is not even a political decision or something like that. So we simply took and measured the times. The initial implementations actually used Java. I think, yeah, it was 1.7, new at that time, so 1.8 didn't even show up, and what we figured out that we have problems with garbage collecting. It literally, whatever you gain, it kills. Whatever you gain, it kills, and you have a lot of requests, it's high processing, and a lot of objects are created, and then when the garbage collector kicks in, everything goes bad. Also, Java has sometimes, I'd say most of the times, has problems with sockets. They're slow. Opening a socket in Java takes around 1 millisecond. We cannot afford that. And there's also one thing which is also important to mention. This can work through TCP/IP, no problem. But it's much better to use Unix domain sockets for this. That's one of the things we didn't employ Java, because Java does not support Unix domain sockets, and third-party libraries that said that they support it were not so good. We needed a sheer performance computing-wise. Anything else? Any other questions? Okay, then once again, thank you for attending and listening to me. Again, I hope that I didn't bore you to death, and I would like to invite you in our cantina to take some beer and some Coke, and there's some sandwiches. So once again, thank you very much.